Okay, so moving on, we have a spring system, a mass spring system. And again, what happens is if you move this here, the system is going to pull this towards this one. It will compress and then it will move again. And so it becomes periodic motion. So it moves this way. You've stretched it this far and then release it. When you release it, the spring will pull it towards the left. But as it goes to the left, the restoring force now becomes positive, so it will push it towards the right, and so on and so forth. And if there is no friction, then this continues on forever. It just moves forward, downward, forward. Forward and then backwards, forwards, and then backwards and forwards, and backwards and forwards, and then backwards. Because again, the equilibrium is here. Okay? So again, we have established that again, we can calculate the restoring force, which is this. And from that, we can calculate the acceleration, which is the restoring force divided by the mass of whatever is attached there. But again, the problem is because this x is always changing as it moves, this acceleration will also be changing as it moves. And because of that, we cannot determine distance simply by this familiar concept that we have already known, which is if we get the initial velocity times time plus 1/2 a t squared, you just get the volume. Again, this does not work because this only works for uniformly accelerated motion. So we have to look somewhere else. If we want to know the displacement, where the object is, we have to look somewhere else. Okay? And one thing that we notice is this motion is always back and forth. It's going somewhere to a maximum distance and then goes back to some place, and then so it's always equilibrium to maximum to the, it's always from the equilibrium maximum to the positive direction, then equilibrium, then maximum to the negative direction, then equilibrium, then maximum to the positive direction. So it's always repetitive. It always moves from this point to that point. Okay? Now, what example can we have that goes back to its original point also? Well, the easiest one is a circle. Right? Because if you have a circle, if this is point A and this is point B, if something is going around in circles, then it goes back to A, B, and then back to A, B, and then back to A, B, and then back to A, B. Now, at first you might say, okay, sir, how is that circular motion related to this? Number one, it's also repetitive. See, its motion is repetitive. It goes from point A to B, point A to B, point A to B. That's just like this one. Goes to point A to B, and then point A to B, point A to B. And in fact, the neat thing to do here is if you have a circle, right? And I'm not sure if I can do this. If you have a circle, so notice my pen. My pen will just be moving around, right? Now, I'm going to do something weird, which is make this slanting a little bit like that. And then now, I will put it completely on its side, right? And then I will still make this one go in circle. So I hope you notice what happened, which is if I look from the side, this pen goes around in circles from A to B. If I look from the side, it's as if the pen is just moving forward, backward. Right? When in reality, it's really making a circle. See? The pen, viewed from the side, seems to move towards the right and left and right and left and right and left and right and left. Okay? Meaning, we can use this property of a circle to describe this. Because if you look at the something doing circular motion from the side, again, something that's doing circular motion, but from viewed from the side, it's as if that pen is just moving forward and backward. So therefore, we can model, instead of pursuing this equation, which is difficult because the acceleration keeps changing, we look at it and say, wait a minute, that's just like the x component of the circle. Right? If I have a center of the circle here, and then that's the x, and this is the y component, x and y, then this moving forward and backward is really just something doing in circular motion, but we don't consider the y-axis. Again, it's tantamount to saying that it's moving in circles, but we are looking at it from the side. So from the side, it looks as if the pen is just moving forward and backward, meaning we ignore the y-axis. Okay? So now we have a connection between why simple harmonic motions like a spring mass system is connected to circles. Okay? Next part is we have to review your angles. Okay? So let's say this is let's take that circle. And then let's take this. And then that is obviously the radius of the circle. Right? You know that. And then what I can do is I can say, well, let's take the x component of that circle, which is this one, x. So that's r. This is r along x. And this is r along y. Okay? And if you notice, that creates an angle here. And if that is a right triangle, right? Because remember, y and x have to be 90 degrees. So that's a right triangle. So therefore, this, from the perspective of the angle, is the opposite side. And this is the adjacent side. Okay? So, knowing what we know about trigonometry, we know that cosine is opposite over hypotenuse. And sine is opposite over hypotenuse, while cosine is adjacent over hypotenuse. Meaning, if I want to calculate adjacent side, then this rearranges and becomes adjacent side is equal to cosine of the angle times hypotenuse. Okay? So why are we trying to get the adjacent side, the Rx? Because again, if you look at this harmonic motion, it's moving forward and backward. It's just like the x component of a circular motion. So if you take the circular motion, you ignore the y component, you ignore the moving up and down, then again, just like looking that circular motion from the side, it moves forward and backward, and that forward and backward is along the x-axis. So you have to get the component. So therefore, this adjacent side is really cosine of the theta times the hypotenuse. Obviously, the hypotenuse there is r, so that would be r cosine theta. That will be Rx. And in a similar manner, Ry, because opposite side is sine, it will be r sine theta. Okay? That's the idea. Now, let's make this simpler. How do I make it simpler? Well, this R could be anything. Could be 10, could be 20 centimeters. But for simplicity, let's make this 1. If we make this 1, then this becomes 1. This becomes 1. So therefore, this becomes cosine theta, and this becomes sine theta. Okay? So again, it means that this side here, instead of r, we say if this is 1, then this side will just be cosine theta, theta being this angle here. This one will be sine theta. Okay? So, take note that our premise was, if you look at this harmonic motion, it's just the x component of the circular motion. So the cosine part. Okay? So, if, for example, this circle is 1, right? And this is 45 degrees, meaning it's halfway, and this radius rather is 1, then I know that this will be cosine of 45. So you just take a calculator, take cosine of 45, and that will be the length of this one. Okay? So therefore, we can get the x as simply the cosine of the angle, if we assume that the radius is 1. Okay? Now, okay, sir, that is the x, cosine of theta, so it's here. But this object is moving, right? It's moving. It's changing. Right? So if it's changing, then it's not just cosine of theta. I mean, it's still cosine of theta, but remember this is doing circular motion. So meaning, this angle is changing. Right? So what I mean by that is, maybe, let's make this bigger so that it's clearer. Maybe at time 0 seconds, it's here, right? Then at time 1 second, it's here, because remember, you have to make a circle. So at time 1 second, it's here. T equals 1 second, t equals 0 seconds. So therefore, at time 1 second, this angle is different. We call it theta 1, or theta sub 1. While at time 2, that theta will become bigger, theta sub 2. So it keeps on changing. Obviously, the angle becomes bigger, and then makes a rotation like that, and so on and so forth. Right? So, another thing to consider, therefore, is how fast this circular motion happens. So how fast is it doing? Because, for example, if the speed is 15 degrees per second, then at time 0, therefore at time 0, if the angle is 0, then at time 1 second, the angle will be 15 degrees. At time 2 seconds, the angle would be 30 degrees. That's what is meant by 15 degrees per second. That's the speed of rotation. Speed of rotation. But that speed of rotation is measured in how much angle is rotating, how much angle is covered per second. Okay? So therefore, we call that angular speed. How fast is the angle changing? So again, very simple. If you say 15 degrees per second, meaning every second that passes, 15 degrees is changed. So at time 0, it's 0 degrees. At time 1, it would have moved and created 15 degrees angle. And at time 2, it would have moved and created 30 degrees angle. Okay? So, there is this angular speed. Okay? So once we have established that there's an angular speed, because after all, it's rotating in a circle, What is the angle at any given time? Well, it's just angular speed times time. Okay? Dun sa mana, sir. Well, again, let's say the angular speed, this is the notation for angular speed, is 15 degrees per second. It means at time 0, the, or let's make it a table so that it's easier, time and then the angle. Meaning at time 0, it's at 0 degrees. At time 1, after 1 second, it would have become 15 degrees. At time 2, it would be 30 degrees. At time 3, it will be 45 degrees. So if I know the angle, if I know the angular speed, I just know what time I'm trying to know. For example, if I want to know the angle at time 2, simple. I get the angular speed, 15 degrees per second, multiply it with time 2. Because I want what happened, what's the angle at time 2 seconds. So this cancel out, that gives me, that gives me 30 degrees. So you see, at time 2, it's 30 degrees. Okay? So, we cannot just use angle because angle means static. Meaning, isa ra ka angle. It's 45, 45 ra. Kung 15, 15 ra. But again, because we are dealing with circular motion, as the thing circulates or rotates around the circle, that angle will be changing. So we have to use this term. We can still find out the angle, but at specific times. So angular velocity times time. Okay? So we put it here that any angle at any time is equal to the angular velocity times time. Okay? And then again, remember the triangle? This is R. The x side is R cosine theta. The y side is R sine theta. We are not interested in the y because again we are looking at the x, only this forward, backward. So we want this. And again, to simplify, if this R is 1, then this is 1 cosine theta. But again, because R could be anything. It could be, it's not just 1, it could be 2, depending on how big the circle is. If the circle is, of course, like that, then the R is smaller. If the circle is bigger, then the R is bigger. Right? So, to generalize it, let's just call it A. So therefore, this will be A also. Instead of, it is R, this is R cosine theta, so A cosine theta. Okay? And then again, the problem with that is this theta is static. Static meaning it's not moving. So therefore, we need to express that in terms of angular momentum, because angular velocity, angular speed, because again, this thing is moving. So therefore, instead of saying theta, we just say Wt. Okay? So finally, we have this format. A cosine Wt. And A cosine Wt. By the way, this cosine is cosine of this because this Wt is an angle, right? So just to emphasize, I'm putting this under parenthesis. So it's just like cosine of 15 degrees. So this will end up in degrees. So this is now the side, the x. This is now the x. So what's this x? This is the distance from here to here. So therefore, okay? So this is now the second equation that we have to know in simple harmonic motion in a spring mass system. The distance is equal to the A, whatever that A is. A depends on a lot of things, right? But we will get into that later on. And then cosine of whatever the angle is. But again, I cannot just say cosine theta because theta means it's not static. But if you say WT, angular angular speed times time, then that means the angle is changing depending on how fast that angular speed is. Again, it's a very simple concept to, again, at first it might be difficult, but when you say 15 degrees per second, it means the rotation is every second that passes, it would cover 15 degrees. Obviously, you can express the angle also in radians, but for simplicity's sake, let's just use degrees first. So this is the idea. This is why, if you want to know the distance, right? So essentially, that's a distance. Again, you cannot use this because this implies that there's a fixed acceleration. But again, as I showed you before, the acceleration is not fixed because this restoring force is not fixed. Sorry, negative kx. This restoring force here is not fixed. It depends on the x, and x is always changing. So therefore, instead of forcing the issue, we looked into how this forward and backward relationship is with circular motion. And again, the relationship is every time there's a circular motion, right? If you look at it from the side, this object seems to be moving forward and backward, but in reality, if you look at it from the bird's eye view, it's really doing circular motion. So therefore, pwede di ay, na you take the rules of circles, of rotation in circles, and then just ignore the y-axis, look at the x-axis. And since in a circle, since in a circle, you have this radius and then you form a triangle, and that right triangle, this side, which is the x side, which is what we are interested in, is the cosine side because of rules of trigonometry. Then we can just say, well, this side is whatever this is. If this radius is a, that's a cosine theta. But again, theta is useless because theta is fixed. So therefore, we need some sort of motion. So again, that's the concept of angular speed. If the angular speed is 15 degrees per second, meaning every second that passes, the thing sweeps 15 degrees. So therefore, if we express, instead of a cosine theta, we express theta as angular speed times time, then this is now a moving system. This is now a moving system. Okay? So that's the idea. So let's spark that idea. And again, let me, at first you might say, kuya, wag good. It's not that convincing, sir. But let me convince you that this is true. Again, so the idea is you can get the distance of that mass is wherever here by saying a cosine wt. Okay, so let's explore. Well, ultimately, this would become an angle, right? So it will be 0 degrees, 2 degrees, 0 degrees, 90, 180, 270, 18, and then 360, right? And then it goes back to 0 again because remember there's 360 degrees. So let's say, let's take a look at the extremes. Let's take a look at cosine of 0, cosine of 90, cosine of 180, cosine of 270, and cosine of 360. Because these are the angles, diba? 0, and then you have 90, and then you have 180, then you have 270, and then 360, which is actually the same. This cosine 0 and cosine 360 are just the same, right? So let's pull up a calculator app. If I have here. And I don't know, does this have scientific, right? And let's take a look at it. So let's say cosine. Cosine of 0. So 0, and then we press cosine. 1. Okay? So cosine of 0 is 1. How about cosine of 90? Well, in this case, I just have to press 90, this calculator, and then go to cosine. Guess what? It's 0. Then 180. 180. And then I'll take the cosine. It's negative 1. Weird, but let's take that. 0, 0, 1, negative 1. Then 270. 270. And then cosine. That's 0 again. And obviously, if you take 360, which is just the same as 0, and then you take the cosine, that's 1. Okay? So, why do I say that this proves that this is correct? Well, let's take a look at the circle. If this is the circle, right? Angle 0 means it's still here. It's not, it has not rotated yet. Right? It has not rotated yet. So, at angle 0, this is 1. So this whole thing becomes 1. So if that thing becomes 1, 1 times A, it becomes A. So that's the maximum. Right? So again, if you look at just the x from the x perspective, that's the maximum. It's here. Now if we look at cosine 90, 90 degrees means this has rotated and already reached here. This red part. And what is that? Well, if you look at it from the side, right? So it's rotating from here. From the side, it's now at the middle. 0. So this whole thing becomes 0 times 1 becomes 0. So the displacement is 0. Here. If it is 180, it becomes negative 1. So this whole thing becomes negative 1. And guess what? Negative 1 times A, it becomes A. So therefore, because remember, 180 is 90, 180. It's here. Let's use the black one for this one. This is 180. So again, from the perspective of the circle, it's rotating here and like this. So when it gets here at 180, guess what? If you look at it only from the side, again, look at this pen. It is the furthest it can go to the left. What's that furthest? What is that? That furthest distance you can go to the left? It's here. So you see, this system mimics this by leveraging what we know about circles, leveraging what we know about trigonometry. We can just say, okay, I can just describe the distance here using A. And if you notice, what is A? A is this to that. So that's your maximum amplitude. That's your amplitude. Meaning the furthest you can go to the right and the furthest you can go to the left. So again, appreciate how beautiful this is. That because we know something about circles, because we know something about trigonometry, we can then describe this periodic moving forward and backward of a mass spring system by using this equation. Okay? So with that, let's close this video and let's finish this video and just say the distance of that mass, whether it goes to the right or the left, is defined by A cosine WT, omega T, where this um, um, where this is obviously the angular speed. How fast the rotation is happening in the equivalent circle that we use to model this system. But again, take note, we are just using that circular motion to model this system. What we do is we take that circular motion and then we ignore the y component. Again, because again, if something is moving in a circle, if you look at it from the side, it's as if, meaning you ignore the other dimension, it's as if the object is moving forward and backwards, just like what we have here. Okay? And then, if you notice, well, this is time. This is how much time has passed when it started rotating. Okay? And then, this A here is obviously the maximum amplitude. That's the maximum. So, if the maximum amplitude, meaning you stretch it to here, which is the maximum, at 15 centimeters, then this is 15 centimeters. Okay? So that's the idea. Now, obviously, there are some limitations here, and the limitation here is we assume that when the object is rotating, it started from 0 degrees. Right? So we assume that we start from 0 and so on. What if, sir, it doesn't start from 0? That we need to modify this. We just have to say A cosine whatever that angle, but if that angle is not 0, there must be some angle that you have to add, and usually we denote that as phi. But again, if this phi is 0, meaning there's no phase angle, meaning it doesn't start at somewhere else, but it starts at 0, this whole thing gets reduced into that. Okay? But I guess I just want you to understand how beautiful it is that out of our knowledge from trigonometric functions, from how circle works, how dimensional analysis, how dimensions x and y are, you can treat them as differently, you can ignore the y-axis, we can model how this moves using that. So again, in books there are two equations that appear. Either this assumes that you start from 0. The rotation starts from 0 degrees angle. Obviously, if it doesn't start, you have to add an angle, and that angle is exactly where you start it at. So if the motion starts here, for example, then that angle is 45 degrees, so you just have to add that, and that is the phase angle, what we call the phase angle. But I hope you understand now why this equation becomes like that, and why can't we just use the equations that we already know, which is, VIT plus 1/2 AT squared. Because again, this doesn't work. This only works for uniformly accelerated motion. For simple harmonic motion, the acceleration is governed by this negative kx, but since x changes, then this whole acceleration changes, and this doesn't work because this works only for uniformly accelerated motion.